In our last video, we established some of the equations we need to analyze a symmetric laminate that's been subjected to in-plane loading, and so let's look at an example here. So here's our example problem. We've got a 4-layer carbon epoxy laminate with plus 30 and minus 30 degree layers, and from the top to bottom 30, minus 30, minus 30, 30. So it is symmetric, and we can write it as in the brackets here 30 / minus 30, and then put a little s on there. The s means that it is a symmetric laminate. And so there's a diagram of that. We're going to apply a load of 500 pounds per inch in the x direction. Here are the properties that come off of the summary sheets for carbon epoxy, and we'll assume that each layer is 5/1000 of an inch thick. And again, our loading 500 pounds per inch is the stress resultant in the x direction. The other two are equal to 0. And so we want to find the mechanical properties excuse me, of the laminate, as well as the the stresses in each layer in the local and global coordinate systems. So let's start out by forming the stiffness matrix. And in addition to those properties that we showed on the last slide, we need the Poisson's ratio 2:1, and we get that from the ratio here, E2 over E1 times the Poisson's ratio 1:2. That comes out to be a pretty small number. So if you stretch this in the transverse direction, the fibers resist any contraction, so that's why that's such a low number. But the quantity 1 minus nu12 nu21 comes out to be just slightly less than 1. So, for example, Q11 here is E1 divided by this quantity, so it's just slightly more than the E1 value of 20 million psi. This one's just slightly more than the E2 value of 1.2 million psi. So now we can transform that with the equations we've developed into the Q-bar, or the global stiffness matrix. And for the plus 30 we've shown here, and for the minus 30, that matrix looks just the same except for the 1/6 and 2/6 terms where it's just the sign that's different. So we use those to formulate the extensional stiffness, or the A matrix. And so we take the Q-bar matrix of each layer, multiply by the thickness, and then sum those to find the A matrix. And so we have 4 layers, each 5/1000 of an inch thick. But you notice here we're just adding these, so the plus 30 Q-bar here and the plus 30 Q-bar here, we can just combine these and just treat this as though it were 2 layers, each 10/1000 of an inch thick instead of 5/1000 inch. And this is important to realize. You're going to make a spreadsheet that you can analyze up to 4 layers, but you can have 100 layers, and as long as they have as they're common, that is, if it's all plus or minus 30 degrees, you can analyze it as though it were just 2 layers, as long as those layers are distributed in a symmetric manner. So with the A matrix, you can always group the thickness of similar layers. Okay, so once we've done the calculations on those, there's the A matrix. What you notice about that is, as we noted, the Q-bar matrices, the 1/6 and 2/6 terms for the plus 30 and the minus 30 had the same magnitude but opposite signs, so they've canceled each other out, and we end up 0 there for a balanced laminate. And when we take the inverse of that, those 1/6 and 2/6 of the inverted matrix will be 0 as well. And notice the units here. For the A matrix, we took the stiffness matrix in pounds per square inch, multiplied by thickness in inches, so we end up with pounds per inch. And when we invert that, the units now are inches per pound. And here are the equations for the laminate's mechanical properties. Starting with EX, we can calculate that as a little over 7 million psi. So in the fiber direction, the modulus is 20 million psi. But when the angles are plus or minus 30 degrees relative to the long axis, you can see that number drops all the way to 7 million psi. This should say EY. I've got a typo here. and that value is about 1.5 million psi. The Poisson's ratio, nu xy, when we calculate that, comes out to be a very large number, 1.35. Now, when you looked at isotropic materials, you found that the Poisson's ratio was always between 0 and 0.5, so not so with composite materials. And here's the shear modulus, about 4 million psi. And we can also calculate nu yx based on that similar ratio that we had for nu 2,1. In other words, ey over ex times nu xy gives us nu yx. So those are the mechanical properties of the laminate. Okay, so now that we have the inverted A matrix, we can multiply that by the loadings, the stress resultants, and come up with the laminate strain. So we've shown those, with the naught superscript, but remember that just means those are the midplane strains. And in this case, if you have a symmetric laminate in plane loading, the strains are going to be the same throughout the laminate. And so you can see again the units, inches per pound, multiplied by the stress resultants in pounds per inch. You're going to have dimensionless strain values then. And one thing you notice about this is that the magnitude of strain in the y direction is greater than the magnitude of strain in the x direction. And again, that goes back to that Poisson's ratio that's greater than 1. As we stretch this in the x direction, it will contract more in the y direction than we actually stretch it in the x direction. Okay, so now to find the stresses, a couple of ways we can do that. We can use the Q-bar matrix with the global strains. But what I prefer to do is to transform the strains into the local coordinate system. So using the T2 matrix, we do that. So this is for the plus 30 layers. Once we have the strains in the local coordinate system, we just have to multiply by the Q matrix to get the stresses in the local coordinate system. And those will be the ones that we're most interested in when we apply failure criteria. Those are the stresses we're going to be looking at. But let's go ahead and find the stresses in the global system as well by multiplying by the T1 inverse matrix. And you can see 25,000 psi in the x direction, 0 in the y direction, and 10,000 and some psi is the shear stress tau xy. And again, this is for the plus 30. I'm going to do the same thing for the minus 30. You'll see that the stresses in the xy coordinate system come out to be the same except for the sign of the shear stress tau xy. And we can do a quick check here, because remember our definition for the stress resultant. It is the resultant of the stresses in the x direction. So if we take the stress in each layer, multiply by its thickness, and then sum those, then that is by definition the value of the stress resultant. So in this case, we've got all three of the stresses times 10 thousandths of an inch for each layer. And so for the n sub x, that's going to give us 500 pounds per inch. Of course, 0 in the y direction in both layers. And because the sign of the shear stress are different, that gives us 0 value for n sub xy as well, so it does match up with the applied loadings. Let me switch over really quickly here to a spreadsheet. And you can see how I like to lay out the spreadsheet with everything here on the left is by layer. So I've allowed for 4 layers, but again, I only have to put in 2 because it is symmetric. So I can put the total thickness of the plus 30s, the total thickness of the minus 30s in these 2 columns. The loading goes over here. So everything on the right of this line applies to the laminate. Everything over here is layer by layer. And again, I like to do it in columns like this. So, for example, the Q matrix is just as shown here. The Q bar matrices, I've done those in closed form as well. And when you do this for one layer, of course, you can just copy them over to the others. And here I've taken the Q bar matrix terms and multiply them by the thickness all the way across, and then those get summed up into the A matrix right here. That matrix gets inverted. The inverted A matrix gets multiplied by the loadings, and that comes up with the strains in the global coordinate system. Then for each layer, we will transform those strains into the local coordinate system and do the multiplication by the Q matrix. Again, you see I'm just doing this term by term rather than do it as a matrix, so I can keep it in a column, copy those over, and again, there's our, after the transformation, those are our stresses in the global system. So there's a couple other layers here, but notice because I put 0 thicknesses in here, they're not impacting anything as far as the A matrix goes. So these are the only two that I'm interested in right here. But as I mentioned earlier, if I make this 0.005 and look at the, because we actually had 4 layers, and still make it plus 30 and minus 30, you'll see that when we do that, we have exactly the same properties, exactly the same stresses. So remember, when you have, as long as it's symmetric, you can group like layers. And so again, you can do 100 layers as long as there are only 4 unique layers as far as material and angle goes. You can analyze them with a spreadsheet as simple as this. And so the next video, we're going to look at some different kind of loadings and see what the stress resultants are from those, and then based on that, do a few more examples.